Morning. Hey.
Good morning.
How are you?
Good. Just arrived at school.
Where are you? Oh, is that the
At
science
Sear
building?
right now.
Is it the science building?
Yeah, in the Sewell Hall.
Ah. Yeah.
Pretty cool in here.
I didn't recognize the poster in the back, but I recognize the doors.
Yeah, that's not sure what that's for. There's like all like the things on the
there
wall.
they are.
All the elk.
Now I
The
know
deer.
where they are. Yeah. Is it pretty pretty quiet there? Because there's no classes like really in session.
Yeah, at this time it starts to get a little busier, and then I have some friends that usually come in and sit with me in like probably 10-15 minutes.
So all that's going to change next week, because they put out an email saying next week is the week to, come on back to campus.
Oh, really?
Yeah.
Like everyone's coming back?
Well, the classes that were supposed to be on ground,
Uh-huh.
but we had to go online for the beginning of the semester, so they'll all be coming back.
Oh, okay.
Yeah. And just
Oh, yeah, I think.
just so you all know, unlike the high schools, we do not have all next week off. So we only have Monday off. Monday the 21st. Oh, got more people in. Good morning. How are y'all doing?
Did you say the high school gets all of next week off?
Oh, some of them do, yeah.
Oh, man.
I think, well, I passed by one of the high schools this week and the parking lot was empty, so maybe they have this week off. Anyway, we don't have a whole, Sierra College does not give you a whole week off for President's Week. Only a single day. Well, why don't we get started? So, a couple of years ago, I went to one of those interactive science museums with my kids. And I saw an exhibit that looked kind of like this. This is not exactly it, but the idea was you pedaled this bike, and the faster you pedaled, the more these lights turned on. And the idea was to show how kinetic energy, like pedaling, can be turned into electrical energy. There we go. In order to turn more of those lights on the faster you pedaled. And it's an interesting exhibit for the kids. This is not a picture of my kids. This is just a picture I found on the internet. So this is a photograph, kind of like the one that I saw. But it is an interesting way to show how the faster you pedal, the more energy is being produced. And so we'll get to that in a little bit, where I want to show you, there's a box down here you can barely see, but this box basically contains a control circuit that lights up more lights depending upon how fast you pedal. And I got to wondering, as a computer programmer and a hardware guy, what's going on inside that box? How does it know which lights to turn on here? And so we'll do that as an example towards the end of the session today. But I guess we'll start out with a couple of warm-up problems. Here are two Boolean expressions, and we want to simplify those using Karnaugh Maps. So just as a review from last time, we have 3 variables, which means we're going to end up with 8 boxes. A 2x4 grid would be ideal for this. And then down one side, label one of the variables, and then across the top, label the other 2 variables. And then don't forget to do those pairs of variables as a gray code. We got our grid now. Now go ahead and for each one of these terms, put a dot in the grid and then circle them. So pair up the circles if you can, or if there's a group of 4, you can circle all 4 of them as long as they make a square or a nice rectangle. And then see what you get as far as a minimized expression. And then try out the one below. The one below has 4 variables, and it's not in sum of products form. So we'll have to do a little bit of work up front in order to get it to sum of products form. In fact, why don't we just go ahead? We'll do that right now. And it's got 4 variables, which means you need to have a grid with 16 boxes in it. I think 4 by 4 would be pretty good. So draw a 4 by 4 grid, and then label 2 variables down one side and 2 variables across the top. Don't forget to put gray code for the not symbols. And then try to fill in the corresponding boxes with dots, and then see if you can circle them and come up with an expression. And then maybe put it in the chat, the answer that you get. I'll start drawing out the grid. Have you got anything for the first one yet? While you're working, I'll start working on the first problem. I feel like I feel like I got some of these in the wrong spots, but I think they're right. Okay, for the first problem, I got these 5 dots placed in the grid. Those are based upon each one of these terms. And now I need to go about circling them. So let's tackle maybe this one in the top left. So that's neighbors to the one to its right, and it's also neighbors to the one below it. You can kind of take your pick which one you want to circle. I'm going to go with the one below it. Now I've got 2 out of the 5 circled, so let's turn our attention to another uncircled one. How about this one right here? So that's neighbors to the one to its left, and it's also neighbors to the one to its right. I can't circle all 3. I have to circle them in powers of 2. So 3 is not one of the options. And I did say that making the circles as big as possible was a goal, and also overlapping was okay. But you really just want to circle all the dots using as few circles as possible. So here I would opt to circle it with the one to its right, not to the one to its left, because that one's already been circled. Now I would circle it to the left if I could make a group of 4, but since I am stuck with a group of 3, I have to do it as basically 2 sets of 2 circles. And then finally I've got this dot down here in the bottom right-hand corner, and it would look like that one's alone, but it's actually neighbors with the one to the left, wrapping around. So let's do a circle that goes off the edges. And now that leaves us with 3 circles. We've got the one on the left-hand side, we got the one across the top, and then we got the one that goes around the edges. So the one that's over on the left-hand side is in the YZ column. So that'll be the term for that circle. And then the one across the top is in the X, not Y set of boxes. So it shares X in common and not Y in common. And then finally the one that goes off the edges is in the not X row, and it also shares Y in common. And then just connecting them up with pluses, and you're done. Now for the bottom one, we've got 1, 2, 3, 4 terms. This one involves all 4 variables, so let's see where that would go. That's going to be on the M not N row, which is this one, and it's going to be in the not O not P column, which is this one. So there's going to be a dot right here. Now the next term only has 3 variables, so I know that means it's going to end up with 2 dots. Anyway, let's take a look where it is. So it's going to be in the MN row and the P column, but P occupies the left column and the right column. So there's going to be a dot in the top left and in the top right. Next term, M not N O. So I look for M not N, which is this row, and the O column. The O column are the first 2 columns. You can see there's O right there, and there's O right there. So we've got M not N, which is this row, and then these 2 columns, and it will go in these 2 boxes. And then finally, not N, not O. Not N is these 2 rows. And not O is these 2 columns. So it's going to occupy these 4 boxes. Let's put a dot in those 4 boxes. So there's already one here. Then we'll put one here, and one here. And now let's start circling. Now I see a group of 4. Actually, I see 2 groups of 4 right off the bat. So I'm going to circle this row, grab all 4 of those. And I see another group of 4 right here. And then what do I do with this one in the top left? Well, remember about the wraparound thing. It wraps around to the one to its right. And it's also neighbors to the one below it. So I could make a circle that grabs these 2, but I could do better than that. Notice that this dot here is also neighbors with the one below it, and this dot is neighbors with the one below it. So I could really grab another group of 4. So incidentally, not only do these Karnaugh maps go off the edge, either way, to the left or to the right, but they also go off the edge top and bottom. Okay, so you can not only wrap around left to right, you can also wrap around top to bottom. Okay, finally, we've got a big long row. We've got that square, and then we have the one that wraps around. So the big long row is M, not N. So this row here occupies just this row. And then this square right here, which is this one here, occupies the not N rows and the not O columns. And then finally, the wraparound square is the M rows and the P columns. And then just connect them with pluses. I'm just going to put a note here to remind you to do gray codes across the top and down the sides. All right, here's another problem. Are these 2 expressions equivalent to each other? Now we have many techniques at this point to be able to determine if they're equivalent. One technique is simply to just construct truth tables for each one of those expressions. Another one would be to simplify both expressions and see if you arrive at the same simplification of them. And another would be to do Karnaugh maps, which is really just a visual way of doing the simplification. But since we're studying Karnaugh maps right now, let's do it that way. So we can show that these 2 expressions are equivalent if we simplify them using Karnaugh maps and we arrive at the same simplified expressions. Expression number 1 is already in sum of products form, so that one's okay. Expression number 2 needs to be put in the sum of products form. Let's do a little bit of work in order to get it there. So now that it's in sum of products form, both of them are in sum of products form, we can start drawing the Karnaugh maps for both of them. Go ahead and take a moment to do that. It's only 3 variables, so each one of them is just a 2x4 grid. Now, since we're trying to show that they're equivalent, it might help if you make sure that both of the maps are labeled identically. So choose which variable you want to put down the side, choose which one you want to put across the top, and then mark the gray codes in identical fashions. So here I've drawn the grids for both of them. I'm going to start putting in the dots. I put in the dots for the first one. You know, I feel like putting the dots in for the second one before I go and circle anything. And look at that. I put in the dots for the second one, and now I end up with 2 Karnaugh maps. They're not completed, but they ended up with the dots in the same boxes, which means had I gone through and ended up circling some of the dots and then writing out the simplified expressions, I would have got the same answer for both of them. So I can really actually just stop here. I can see that the dots are in the same boxes in both grids, so these 2 expressions must be equivalent. And really, a Karnaugh map without the circles, a Karnaugh map with just the dots in it, really is just a truth table. But instead of being a one-dimensional truth table going from top to bottom, it's a 2-dimensional grid, and we just put dots in the boxes where there would have been a 1 in the output column for a truth table. So a Karnaugh map really is just a 2-dimensional truth table. So here's another problem to do. We've seen one like this. I give you a truth table, and you need to construct a circuit from this. So we're going to do this by making a Karnaugh map, coming up with a simplified Boolean expression, and then drawing the circuit out of ands, ors, and nots once we get there. Just like before, focus your attention on the rows where there is a 1 in the output column. The nice thing about using Karnaugh Maps for this is that once we write out the expressions for each one of those rows, it will already be in sum of products form, and we can then just plug the dots directly into the grid. Okay, so the expression for this first row is this row is a 1. The output is a 1 when A is false, B is false, and C is false. So that's going to be not A, not B, not C. You can almost just take these patterns of zeros and ones and translate them directly into the expression. If there's a 0 in the column, you just put a bar over the variable. And if there's not a 0, if there's a 1 there, then you just leave the variable as is. It's very simple. For the third row, we have not A, B, not C. For the fourth one, we have not A, B, C. Row number 5 is A, not B, not C. And the last one is A, B, C. And so there is our sum of products form. So now we're going to do a Karnaugh map, but I'm going to show you a slight variation on it. It's just labeled differently, but it's still the same grid. So the way I'm going to label this is going to make it easier to work with the truth table. Instead of putting A and not A on the left-hand side, and then B and C with a gray code across the top, I'm going to put zeros and ones. So the left-hand side is still going to be the A side, and the top is still going to be the BC side, but I'm going to put 0, 1 on the side, and then a gray code of zeros and ones across the top. Notice that this is not strictly counting in binary. It's not going 0, 0, 0, 1, 1, 0, 1, 1. The 1, 1 appears somewhere in the middle. Now the reason for labeling it like this is I can almost just read off the binary code here. Like this box here in the top left, that's the 0, 0, 0 box. And this one in the top right, that's the 0, 1, 0 box. So really, I can just look at the zeros and ones in my truth table and just transfer them over into the Karnaugh map. So this first row here, where there was a 1, is the 0, 0, 0 box. So I'm just going to put a dot there in the 0, 0, 0 box. It helps to label the variables so they kind of almost go in order from left to right, so you can just read them directly. For row number 3, we have 0, 1, 0. So we got 0, 1, 0. That means there is a dot in the top right. Row number 4 is 0, 1, 1. 0, 1, 1 up here. And then row number 5 is 1, 0, 0. So we've got 1, 0, 0 in the Karnaugh map. And then finally we have all ones, which is down here. Now we just circle them like we did before. So I see a pair right here on the left. I see a pair here in the middle. And then this last one, we have a choice of what to do. We could either circle it with the one to its left, or we could go off the edge and circle it with the one to its right. I wouldn't do both because that introduces a redundant circle that we don't need. Remember, you want to use as few circles as possible to circle all of the dots. So you've got a choice. You can either do it one or the other. You'll end up with a slightly different expression, but they'll both be just as simple. circle on the left is the 0, 0 column, which means B and C are both negated. The circle in the middle is the 1, 1 for BC, so that's B and C are both positive. And then this one over here on the right-hand side, that is that is A is 0 and B is both a 1. So A is knotted and B is positive or true. Then just connect it with a plus, and you're done. That's at least you're done as far as making an expression. So now we need to construct the circuit. So we've got B and C both knotted, B and C both positive, and then not A and B. So let's see what we can do here. I'm going to put A, B, and C down the left-hand side, and then A, I'm kind of doing this one here first, goes into a knot, and B does not go into a knot. That goes into an AND, so that forms this term. And then BC here also go into an AND. And then finally, BC get knotted and go into an AND. Kind of like that. And then there's a final OR at the output. So there's your circuit. And this one looks fine. Now, from a kind of an aesthetic point of view, question is, why is there an OR at the end? Because we've got these three terms here that have both been ANDed together. All three of them have been ANDed together. And then there's this OR that goes in between them. So I could do this as two separate ORs, or I can just use one OR with three inputs to it. It gives you the same result. I could have done it like this. Let me just erase some of these wires. I could do an OR here and run these two into it. And then I could do a final OR here and run this one. Oops. Like this. So both will work. Take your pick as to which one you want to use. So aesthetically speaking, this one's a little messy. You've got this stuff going over here. So here's another way to do it, is instead of putting A, B, and C down on the left-hand side, I'm going to put them across the top. And then I'm going to draw these three vertical lines. And I'm going to make basically what's called a bus. So these three inputs are just coming down the side of the circuit. And then I can just pull off the values that I need going to the right. So the first thing I need is an AND with A knotted. So I'm going to pull off A here. And then B just comes straight off. Then I need another one where I got B and C. So here and here. And then I have one more where I have C being knotted. And B just gets pulled off to the side. And then my final OR over here. Okay. So that's the basics of Karnaugh Maps, right? Got a Boolean expression, turn it into sum of products form, make your grid, put in the dots, circle the dots, and then out pops the simplified expression. So now I want to show you some more, what would I say, like practical examples. These are kind of abstract, right? I give you the expression, and then we just make the Karnaugh map. But let's do a problem where we're not given the expression. What we're given is a criteria, a specification for what it's supposed to do. I have to admit, this one's a little made up here, but I want to design a circuit that outputs a 0 whenever you have a month that has 31 days. Now, it seems a little odd to like output a 0 for something, for a condition that's true, but in the field of digital logic, this is called an active low circuit. Again, I'm kind of stretching things a little bit here, but active low is an actual thing. Active low means you output a 0 when something is true, rather than outputting a 1. Active low is fairly commonly used in digital circuits probably because maybe zeros use less electricity than ones do, and so they just flip the logic around. So another way to state this is I want to output a 1 for months with less than 31 days. And so here is the truth table for that. I've got a binary number, a 4-bit binary number representing the number of the month. I'm numbering them from 0. So January is 0 up to 11 for December. And here are the 4-bit codes for those months. And then here are the ones and zeros. So January has 31 days, so the output is 0. February has less than 31 days, so I'm going to output a 1. March has 31 days, it gets a 0. April has 30 days, so it gets a 1, and on down the chart. Just like before, in order to construct this Karnaugh map, we're going to focus our attention on the rows where there's a 1. You also may be wondering, why didn't I just use a 1 for the months that had 31 days? Why did I choose to make it a 0? Well, honestly, it's because the Karnaugh map's more interesting if you do it that way. If I do it with just ones, you end up with a really boring Karnaugh map, and it's not a great example. Okay, let's make this grid. We're going to need a 4x4 grid because we've got 4 variables. Down one side, I'm going to put A, B, and across the top, I'm going to put C, D, and I'm going to do that as the binary numbers because I have a nice truth table that uses binary numbers. So I'm going to make a Karnaugh map that uses binary numbers. Remember to do a gray code. And now we're going to put in those dots. So the first one here is in the 0001 box. So here's 00, here's 01, and we've got a dot right there. And this next one is in the 0011 box. So that's 0011, there's a dot right there. The next one is in the 0101 box. The next one is in the 1000 box. And the last one is in the 1010 box. Okay, so there's our 5 dots. But we're actually not done. See, we had 4 variables as our input, A, B, C, and D, to give us a total of 12 combinations because there's 12 months. But with 4 binary inputs, we've actually got 16 inputs, 16 possible combinations. We're only using 12 of them. There's 4 of them that kind of go unused. But I'm going to go ahead and write those in. So those represent row 12, 13, 14, and 15. So those are the rows for months that don't exist. But we still kind of have to take them into account. Because you see, it's possible that we could arrive at a Boolean expression that is simpler if we take those 4 months that don't exist into account. What we could say is that if the input into this expression was, let's say, 13 for month 13, which would be, I don't know, 2 months after December, we don't really care what it outputs. We don't care whether it's a 0 or a 1 for the output, because it'll never happen. We're never going to have a month number 13. So let's put it into the table, but let's say, look, we don't care. We don't care whether it's a 0 or a 1. I'm going to write that in as an X to say, you know, here's a value that I want to take into account, but I don't care whether the output is a 0 or a 1. Same thing for the other non-existent months. So let's transfer those X's into our Karnaugh map and see what we get. So we've got an X on the 1100 box, which is right here. I'm going to put in an X, not a dot. And then the next one is at the 1101, which is right here. And then the 1110, which is over here. And then the 1111, which is here. So it's a whole row of X's in our Karnaugh map. So this is called a Karnaugh map with don't care. You can actually Google that term. This is a Karnaugh map with don't care. And that is these terms that have an X there. I don't care whether the output is a 0 or 1 because they're just never going to happen. But let's see what it does to our circles. So we're going to treat those X's as if they're a 1 if it allows us to make the circles bigger, and we're going to treat them as a 0 if we get to ignore them. So pick whether these X's are going to be 1s or 0s, or dots or empty, whichever makes the expression simpler. So when we go and circle our dots, we got a pair here, and then for this dot here, we could either pair it up with the one above it, or we could pair it with the X below it and treat that X as though there was a dot there. Now, I think it's more interesting if we circle it with the dot above it. But now take a look at this dot over here in the lower left-hand corner. I could pair it up with the one to its right, which is over on the other side, and that would make a 2 by 1 circle, but I could expand it out to be a 2 by 2 circle. Grab those two x's above and treat those boxes as though there were dots there. Because when I do that, I essentially eliminate one of the variables from that term. Remember, as the boxes get bigger, the number of variables for that term gets smaller. You've probably seen that as you were filling your boxes. If you have 4 variables in your term, then you only put 1 dot in there. If you have 3 variables, you put 2 dots in there. And if you have only 2 variables, you put 4 dots in there. So the bigger we can make the circles, the smaller our terms become. So I'm going to circle all 4 of these. And that should make my expression a little bit simpler. So I'm going to treat these 2 x's in the middle as though they were empty boxes. And I'm going to treat these 2 x's on the sides as though there were dots in those boxes. Okay, the top circle at the circle at the top is on the 0, 0 row, and D is a 1. So that's going to be A, not B, not D. And then this circle, this little vertical one, is going to be where A is 0 and CD is 0, 1. So A is 0 and CD is 0, 1. I think that's right. And I know I'm going to have one more term. I'm just going to slide this over so I got some space. There we go. And then finally, the large box at the bottom is A is 1 and D is 0. So A is 1 and D is 0. And then we'll just connect them up with pluses. And if we hadn't done this giant box with 4 dots in it, if we only done the 2 dots, these here, we would have ended up with A is 1, B is 0, and D is 0. We would have ended up with A is 1, B is 0, and D is 0. So we would have ended up with a term that had an extra variable in it. So by making the boxes bigger, we got rid of one of those variables. And that made our expression a little bit simpler. So I used a program called Logisim, and I built that circuit. I remember I made this bus, you can see it here, with my A, B, C, and D values, and then I just pulled off the values that I needed for each one of these AND gates, and those all flow into a 3-input OR gate, and then here's my output. So I can punch in a binary number over here, representing the number of the month, and then this light should light up according to which the number of days in the month. So this number here represents January. It has 31 days, so the light is off. February has less than 31 days, so the light is on. Here's March. It has 31 days, so the light is off. April has 30 days, so the light is on. And then May is 100, light is off. June, July, August, and then here's September, October, November, and then finally December. So what happens with the other months, the non-existent months? Well, here is month number 12, which is the one after December. it ended up being on. Here's 13, it's off. Here's 14, it's on. And then for 15, it's off. But remember, we don't care. We don't care what the output is going to be because those months just simply don't exist.
So if you hadn't included those months in the group of 4, they wouldn't turn on?
Ah, correct. They would be all off. Because those boxes would have been left empty, and that represents the light being off. Okay, so remember that picture I showed you at the very beginning with the guy on the bike, and he was pedaling the bike and the lights light up? So here's a simple diagram of what's going on inside of that little control box. You've got your bike here, and as you pedal the wheels, the wheel turns, and then it turns this little generator that's attached to the back wheel. So the faster you pedal, the more voltage comes out of that little generator. And let's just say, for sake of this example, that little generator produces anywhere from 0 to 5 volts of electricity. So no matter how hard you pedal it, it maxes out at 5. That represents the fastest that thing can go before it, I don't know, spins apart and falls to pieces. So that voltage then goes through, well, this thing called a tachometer is basically measuring how fast that generator is turning. But the next important piece is labeled A to D. A to D stands for analog to digital. It's also analog to digital converter, or ADC. So its job would be to take the analog amount of voltage and turn it into a binary number. Remember, our voltage can go from 0 to 5. And so in this case, again, for the sake of a simple example, this one just outputs the binary numbers 0 to 5. So anywhere from 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 0, 1, which would be the possible outputs we could get from this. And then
so there's like a preset like rotations per minute that produces a certain amount of volts.
Yeah. So if you pedal slowly, it's producing, let's say, 1 voltage, 1 volt of output. You pedal a little bit faster, it produces 2 volts. And so the ADC circuit just simply measures the voltage and then produces a binary number to represent that. I don't want you to worry about how all that works. What we're concerned about here is this lamp logic that takes those 3 bits of input and turns it into those lights turning on. That's what we're going to work on next. So let's make a table to represent the information that we have here. We've got the voltage, which can be 0, 1, 2, 3, 4, or 5. We can then convert that into a binary number. So we have A, B, and C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and 1, 0, 1. And I'm just going to move this up a little bit. Here we go. Next, we've got these 5 lamps labeled L1 through L5. So those lamps are either going to be on or off. That represents either a 0 or 1. But I don't just have one circuit to turn on 5 lamps. I actually have to have 5 separate circuits, each one of them looking at the binary number and then deciding whether or not that corresponding lamp should be turned on. Let's take a look at lamp number 1, which is the one on the very bottom. If no one's on the bicycle or the pedals aren't turning at all, then that lamp should be off. So we'll put a 0 there. And then if somebody starts pedaling a little bit, then the generator produces 1 volt of electricity. The A to D converter converts that into 001, and at that point, the first light should turn on. So we'll put a 1 there. And that's going to be the case for the rest of the voltages. Like, as long as you're producing at least 1 volt of electricity, lamp number 1, the one on the bottom, should be turned on. Now, lamp numbers 2, 3, 4, and 5, those should all be off when you're not producing any electricity at all. If you're producing 1 volt, lamp 1 is on, and then the other 4 are off. When you're producing 2 volts of electricity, lamps 1 and 2 are on, and the others are off. 3 volts, 3 lamps are on, the others are off. 4 volts, 4 lamps are on, and the others are off. And then 5 volts, all lamps are on. Okay, so we've got ourselves a table of inputs and 5 separate tables of outputs. So we're going to have to make a Karnaugh map for each one of those. I'm not going to show you all 5. I'll do a few of them. But before we do that, take a look here. We have 3 bits of input, of which we've only used 6 of them, 0 through 5. And what about the other 2? What about rows 6 and 7? Well, those rows should never happen. Our little generator just simply cannot produce that much voltage. So we will never get a 6 or a 7 as inputs into our circuit, which means we don't care what combination of lights lights up, because we'll never get those inputs, and so they'll never appear. We're just going to do whatever makes our circuit simplest. So let's do the Karnaugh map for light number 1. We've got A over here on the left, BC across the top. And then we'll put in the dots. Okay, so let's see, where is there a 1? There's a 1 here, 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 and here. So we've got a 1 here, that's at the 0001 box, which is right there. And then we've got a 1 here at the 010 box. And then a 1 at the 011 box. A 1 at the 100 box, and then finally 1 at the 101 box, which is right here. And then 2 X's, 1 at 110 and 1 at 111. So 110 is 110. So there's an X here, and then there's an X at 111. And so now we'll just circle those. Let's see, what do we got? So I see a whole row, a row of 4 right down here. So I'm going to treat those X's as though there's dots there, and that allows me to get a whole row. And then likewise, over here on the right-hand side, I can grab a whole square full of boxes. Now, I've got a group of 6 here. I can't circle all 6. So I'm going to have to group 4 of them together here. So again, I can grab a whole bunch all at once by treating those X's as though there were dots there. And then likewise, I can grab this group of 4 and treat that X as though there was a dot there. And that gives me the expression A plus B plus C. I've got A is positive, that gives me this whole row. I've got B is positive, which is the box on the right. And then I've got C, which is the box in the middle. So that's the circuit, or that's the expression for light number 1. And we just got 4 more to do. I won't do them all. I'm going to do a couple of the interesting ones. Light 4 is kind of interesting. So for light number 4, let's see where the dots are going to go. So here's light number 4. We're looking at this row right here. There's a 1 here, there's a 1 here, and there's 2 X's. So we've only got 4 boxes to fill in. Okay, so this one right here is at the 1, 0, 0 box, which is the bottom left. And then the 1, 0, 1 box for this one. There's one next to it. And then these 2 X's actually just end up going in the same boxes that the X's went into for the first map. So I'll just put them in right there. So I can circle this entire row. And that gives me the expression A as the answer. And then finally, let's do light number 5. So for light number 5, we just have a 1 and 2 X's. This 1 is at the 1, 0, 1 box. Here. And then here's our 2 X's. They just go in the same boxes. And now to circle these, I would take this dot and join it with the X next to it, but I would ignore the one over here on the right-hand side, because I can't circle a group of 3. So I'm going to treat that first X as though there's a dot there. I'm going to treat that last X as though it was empty. And this expression is AC. So each one of those lights gets their own expression. And so we're going to have kind of like 4 little Boolean circuits in order to control these lights. So again, I put this into this program called Logisim. I've got my 3 inputs, A, B, and C, over here. And then here are the 5 lights arranged from bottom to top. So if you're not pedaling, you've got an input of all zeros. Then if you start pedaling a little bit, you'll end up with 0, 0, 1. And then light number 1 turns on. And then if you pedal a little bit faster, you've got an input of 2, which is 0, 1, 0, and now both lights are on, both bottom lights are on. And then pedal even faster, and you've got an input of 3, so now the third light comes on. I colored these dots the same way they're colored in that photograph on that first page. And then pedal even faster, you've got an input of 4, so now we've got these 4 lights on, and then finally, as fast as you can go, you've got all 5 lights on. And then for the 2 inputs that will never happen, those are 6, well, it only turns on 4 of the lights, and then 7 turns them all on. But remember, those inputs are never going to happen. Okay, so that was kind of a couple of real-world examples. And now let me show you one more real-world example. And I forgot to bring it out as kind of a prop. But you've seen those little alarm clock displays, what are called 7-segment displays. They look kind of like this. So you can display the number 0 by turning on these outer segments here. And then 1 looks like that, and 2 looks like that, 3, 4, 5, here's 6, 7, 8, and there's probably 2 ways to do 9. You can either do a 9 like that, or you can do it like that. We'll do it like that. So you need 4 bits of input to produce these digits, because there's 10 digits, so you need a minimum of 4 bits. And when you're only using 10 out of the 16 possibilities, this is called binary coded decimal. So you've got 4 bits of input, but you're only using 10 of the 16 possibilities. If you want to do 2 digits of input, then you set up 2 sets of 4. And this set of 4 represents the first digit, and this set of 4 represents the second digit. So if you wanted to do a number like 37, you'd put a 3 over here, and you put a 7 over here. But if you want to turn that into digits that you can actually see on the screen, on the display, then you're going to need to have a circuit that turns those binary numbers into the appropriate segments being turned on and off, kind of like we did the lights for the bicycle. So you'd go through the same analysis, right? You'd write out a Karnaugh map, or you make a giant truth table, and then you have 7 output columns, and then you do a Karnaugh map for each one of those 7. And you determine whether or not that particular segment is turned on or off for a given input. Give me a moment here to pull something up. All right, got it. So you go through that analysis. Yeah, there's 7 Karnaugh maps to do. But then you end up with something that looks like this. I've got here 4 binary inputs on the left, representing the numbers 0 through 9. And then it runs through this giant circuit. Now, each one of these pieces here represents one individual segment of that LED. This is segment A here, this is segment B, segment C. I got lights on each one of them so I can see whether they're on or off. And then those all wire up into the LED segment itself. And so I've got inputs of 0, 0, 0, 0, and an output of the number 0 on the display. And then if I change this to 1, I end up with a 1 over there. And then here's 2. Here's 3. Here's 4. 5, 6, 7, 8, 9, and then that's it. Now remember, I'm only using 10 out of the 16 possibilities, so there's 6 more left over that I didn't account for. But those represent inputs that just never will occur, never exist, right? For binary coded decimal, you would never input the number, let's say 11, into it, because that just doesn't exist. So let's see what happens if I put in like one of those other numbers. Here I get this kind of strange looking thing. That's for input number 10. For input number 11, you actually get the number 9 again. For 12, you get a different 9 for some reason. And then for 13, you get a 5. And then for 14, you get a 6. And then for 17, you get another 9 again. But again, those inputs would never happen. And so you don't worry about what they actually would output. Let's see, do Nixie tubes work in a similar way? So a Nixie tube is a little bit different. I guess the answer would be no. It does not work the same way. So in a Nixie tube, you actually have all 10 digits stacked up on top of each other as separate wires in there, and then it just lights up a different wire depending upon what its input is. So I guess in one sense, you know, it could work a similar way if you had a binary number going in, 4 pins representing the binary number, and it just lights up one of those 10 wires. But on old Nixie tubes, they didn't have any kind of binary decoding going on in there. They just had 10 inputs. And then depending upon which pin had voltage running to it, that's the wire that would light up. So you'd need another circuit outside of the Nixie tube to actually figure out which one of those to light up. It would basically be a like a 4 to 10 decoder, 4 bits of input going in, and then 1 of 10 wires being turned on. However, Nixie tubes are like, I don't have any, but I'd really like to get some because they're just super cool, right? They got that old retro look to them. Here's one that's arranged in kind of a vertical fashion rather than a horizontal. But you can see all these wires are stacked up inside. There are some kits that you can get. Yeah, there are some kits you can get to build modern like clocks out of these old Nixie tubes. Build it yourself. Yeah, they're kind of expensive because I mean Nixie tubes are not exactly like common commodity products anymore, where they're just they used to be produced, you know, by the hundreds or even thousands, so they were relatively inexpensive. But now they're produced in the like dozens, and so they get to be more expensive. Oh, by the way, you can go and you can buy a chip, a logic chip, that actually does this binary coded decimal to LED conversion. It's a BCD to 7-segment decoder. And here's the circuit that's inside of it. So it looks kind of similar to the circuit that we came up with, in that it's got 4 inputs over here and then 7 outputs over here. So you got a whole bunch of ands in here, and these are actually ors. They look like ands, but if you see these little dots right here on the inputs to them. So if you negate all the inputs to an AND, it becomes an OR by De Morgan's property. But this particular circuit does not implement exactly the same set of outputs that we did. For us, we said we don't care what the outputs for 11 through 16 are. But the way this particular one is set up, it actually does produce like patterns that the designers wanted to make. They wanted to make these little like half boxes. So their circuit actually produces a blank for a 15, and then 10, 11, 12 produce these little half boxes. I don't know what's up with 13 and 14, but that's what their circuit produces, is the numbers 0 through 9 plus some patterns that they were interested in producing. But nevertheless, if you're going to build one of these, you start with a giant truth table. Here's your inputs, A, B, C, and D. Here's your outputs. And then here's just the combination of digits that are going to, or segments that are going to be turned on or off depending upon what inputs you give it. So that's basically some practical examples of using Karnaugh Maps to produce simplified Boolean expressions based upon a specification or a criteria that you want them to behave like. Okay, so we're going to take a little break, maybe about 10 minutes or so, and then when we come back, we're going to go over the programming assignment for this week for the students that are in my class. So it's going to be another Python assignment. We did Python 2 weeks ago, then we took a little break when we did the NAND game, and now we're back to Python again, and we're going to be doing Python now for the next 4 weeks or so to get us up through cryptography. So I'm laying down kind of a foundation for learning just enough Python to be able to write the kinds of programs that we need to write for the next few assignments. So we'll take a little break, and then we'll come back at about 11 o'clock our time.
Recording stopped.
Now, those of you on YouTube, let's see, not much in the way of comments, so if you have any questions, go ahead and ask them now. And I'll get set up for our programming assignment. Alright, so you wanted to see a little of Logisim. So it's a free tool. Just Google for Logisim. You end up on this website. It's unfortunately no longer under development. The person who wrote it moved on to do other things, but he left it in a state where it's pretty much finished. And it's certainly a usable tool. It's used by universities and colleges all over the world to simulate logic circuits. So rather than actually physically building them, you can just run them in the computer. So when you launch it, you get a build area right here. You got a collection of pieces that you can put into the circuit, and then some places where you can change attributes. Yeah, there is another version. People have taken this Logisim, and since the author made it open source, they've taken it and they called it Logisim Evolution, and they're starting to add features to it. Unfortunately, they also took away some features, and so I tend to just go back to the original version because they took away some of the features that I liked. I should play around with the Evolution version again. It's been a couple of years since I looked at it. But basically, you've got gates here, you've got knots, ands, ors, nands, nors, and so forth. And it's not drag and drop. It works a little unintuitively, but if you want an and, you just click on that, and then you can just pop them into your circuit. And then we got inputs here, so we can put a couple of inputs. I'm going to get rid of a few of these, I don't need so many. Hook up an output to this, and then just start connecting them together. Built yourself a simple circuit, and then we can use this hand tool to kind of play around with the inputs and see what would happen. And you can do things like we can analyze the circuit, come up with the truth table, come up with an expression. It'll even do Karnaugh Maps for you. And you can even go in the reverse direction. You could actually start with the truth table, put in the ones and zeros that you want, or x's. So we could even change this around. And then we could say, build this circuit. And then it'll construct the circuit for us. It's kind of like cheating a little bit, but anyway, so you can build up circuits out of the fundamental gates, and you can also use some built-in components that they've devised. Like here's an adder. I can bring that in, and so you've got your two inputs over here, you got your carry in here, your carry out over here, and your sum over here. So I can put an input on it here and here. And then I've also got a carry in here, so let's feed that in there. And then I've got an output here and an output here. So this is just a half adder. Oh, actually, no, this is an 8-bit adder. All I have to do is I have to change the number of bits. Let's see. 8 data bits. I only want to do 1 bit. There we go. So now 0, 0 with a carry in of 0 is 0, 0 here. If I do a 1 and a 0, I get a sum of 1 with no carry. And then a 1 plus a 1 is a 0 with a carry. And a 1, 1, 1 is an output of 1, 1. So I can build actually I think this is a full adder since it involves the carry, and then I can connect these up together. So I could put like 4 of them together and produce a ripple carry adder with 4 bits. And then from there, I can start building other components. Like I've got a comparator, shifters, I've got memories, all sorts of input outputs. I've got a joystick, keyboard, LEDs, 7-segment displays, LED matrix, which you could actually use to produce kind of a rudimentary graphical display, really small graphical display. But you could essentially build a very simple computer out of this. It wouldn't run very fast. It's all running simulated. It runs no more than like less than a megahertz. But you could build a simple computer with Logisim, and it has been done. You can go Google around and find actual working computers built entirely in Logisim. Again, they don't run very fast, but they might be fast enough to play a very simple video game like Tetris or Space Invaders or something like that. That NAND game that some of you did is basically a web-based version of this, what you see on the screen. Okay.
Recording in progress.
So this is lab assignment number 3, and we are doing an assignment called truth tables. So we have been analyzing truth tables and coming up with Boolean expressions over the past couple of weeks, or past week or so. And so now we're going to do it in programming. So we're going to build truth tables using a programming language, in this case Python. And along the way, we're also going to learn about things like how to construct loops, how to construct conditionals, and build slightly larger Python programs. So this assignment is broken up into 3 files. There's 2 lesson files, which are just tutorials, and then 1 actual assignment file. You only need to turn in that last one. So you need to download all 3 of these to your computer and then upload them into the Jupyter environment. So I'm going to go ahead and do that. I'm going to download each one of them. So now all 3 of them are sitting in my downloads folder. And then I'll switch over to our Jupyter environment and I'll upload them. Then we're going to walk through the 2 lessons first and then through the actual assignment. So lesson number 1. I'll kind of walk you through it. I'll kind of read along as we go. If you are doing this, if you're one of my students, you can load these into Jupyter and then follow along. So as we said a couple weeks ago, Python has the usual assortment of operators: plus, times, divide, subtract, and so forth. You've also got integer division, modulo, and exponent. This is a Python notebook environment, so you can experiment with this. One of the reasons why I really like the notebook environment is you can just open up a cell and then type in some Python stuff and just see the results immediately. You don't have to go over to an editor, type in a whole Python program, run it, look at the output, and then try to correlate the output to what you wrote, especially if the program is much larger. So in a Python notebook environment, you can simply type in an expression or a statement, press Shift-Enter or click on the Run button, and then it'll execute your statement. You can just see the results directly. You can always open up a new cell by clicking on the plus button. It'll open up a new cell below where you are, and then you can type in another expression. As you can see, Python readily handles really large numbers. Oh, we got a note here. You can't log into Jupyter. There's no reset password option. Remember, when you did this 2 weeks ago, you would have typed in your username and you would have just picked a password. So there's no a specific account setup page, and there's no page where you go and create a password. The first time you log in, you just enter your MySierra username and you just type in a password you want to use. And then it creates your account using that information. And then from that point forward, it then will use that same password. So if you run into a situation where you typed in a password and you either don't remember what it was, or you mistyped it and now you can't type it in again, just send me a note and I will go and reset your account for you. You won't lose any of your files, but you'll be brought back to the same screen you've seen before where you type in your username and you just pick a password. It's a very simple login process. So send me a note and I'll go ahead and do that. Strings in Python are enclosed either in single quotes or in double quotes, whichever is more convenient. You can concatenate strings together using plus, just kind of like in Java. So now we're going to start talking about variables. So Python is different from Java in that you do not need to pre-declare your variables. You just use them. So if you want to create a variable and assign to it, just say like x equals 5, and it will go ahead and it will assign the value x to 5. You also don't need to tell it what type the variable is. It figures it out. If you assign a string to a variable, then obviously that variable holds a string. If you assign a number to it, then obviously it holds a number. And you can actually change the types later on. I can assign a string to a variable now, and then in the next cell I can assign it to a number, and it won't care. So in box number 7 here, I've assigned the string Sierra College to the variable school, and now I can view what's inside of that variable by just typing the variable by itself in a cell and pressing enter or shift enter, and it will display the contents that are in that variable. You can, of course, assign and display in the same cell. Here's an example of it. So this just is a shortcut for opening up a separate cell to display the value. You can only display one variable at a time. So if you want to display the contents of 2 variables, you're going to have to use 2 separate cells for it. So problem number 2 is to assign the string quoth the raven nevermore to the variable raven. And you want to do it in such a way that these double quotes inside the quotation from the poem are preserved. So the key here is to remember that in Python you can either use single quotes or double quotes depending upon which one is more convenient for you. Since the string that we want to assign to the variable contains double quotes, we would opt to use the single quotes to enclose the string. And that'll ensure that the double quotes stay as part of the string and the single quotes are just used as the delimiters around the string itself. And if we want to view what's inside that variable, we open up a new cell, type in the name of the variable, and then it'll display it, and we can just visually verify that we've got the correct answer. Problem number 3. A certain website requires passwords to be 8 characters long and composed of both uppercase letters and lowercase letters and digits. How many possible passwords are there? You can calculate this number directly in the notebook. So we've got a password that is 8 digits long and can be composed of 26 lowercase letters, 26 uppercase letters, and 10 digits. So there's a total of 62 possible characters we could put in each position of the password. And so it's 62 times 62 times 62 all the way down the line. So it's raised to the power of 8. And that gives you the total number of passwords, assuming that every combination of letters and numbers was a valid password. Let's see how many that is. Whoa, that's quite a few. So getting back to the thing about the strings, yes, 3 quotes can also work. So it's like three quotation marks, quote, 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 and end, quote, quote, quote. You can also do it with double quotes as well. I opted not to bring that up for this lesson, at least, because students who are coming into this knowing probably Java are probably already familiar with like just a single set of quotes. And so we're working with that. What the triple quotes allow you to do is maybe have a string that spans multiple lines. So if you have a whole block of text, then you can start with triple quotes over here, and there's typing all your text, and then triple quotes at the bottom. So problem number 4, YouTube uses a video identifier that is 11 characters long. Each character is either an uppercase or a lowercase letter, a digit, or a dash. How many possible YouTube IDs are there? So you're going to type in the calculation here. Replace this word none with a calculation that'll figure out how many possible YouTube videos there could be. Now, I have down here a box that will check to see if your solution is correct. This is called an assert. This box will check to make sure that the number you come up with is greater than this number and less than this number. Now, obviously, I couldn't put the actual number into this box because then you could just copy and paste it into the box above and you'd be done. So the way I've written it here is if it's in this range, then you probably did the calculation correctly. So you'll type in your expression here, execute it by pressing Shift-Enter or clicking the Run button, and then come down to this box down here and press Shift-Enter or click the Run button. Actually, let's go ahead and do this calculation. So the expression I would type in here would be 26 plus 26, that's my uppercase and lowercase letters. I've got digits, and I've got a dash and an underscore, which is 2 more. And then I would raise that to the 11th power. And then I can also take a look at what the value of this number is. I just opening up a new cell, and there's the number of possible YouTube videos that could be uploaded to that service. Now, and then finally, let's check to make sure it's in the right range. So I'm going to click in the cell with the assert. I can click anywhere in the cell and then press Shift-Enter. And if I don't get an error message, then the check passed. Let's see what it looks like if I didn't do the calculation correctly. Let's say I forgot to put on the +2 here. So I Shift-Entered that cell to rerun it. And then just so I can see what the value is, I Shift-Enter this cell, and then if I Shift-Enter this one, I get an error. So it's a little hard to read this error, but basically it means your test did not pass, and so your assertion failed. You have to go back and recheck your answer. Okay, so if I fix the results and I re-execute the assertion cell, then I get no errors and I know my test passed. So actually, honestly, this doesn't seem like a very big number, but it really is quite big. Let's see, it's, let's see, I'm breaking it up into groups of 3. So there's 3 there, 3 there. So this is millions. No, there's a group of 3, there's a group of 3. So we got, and then here's billions, and there's trillions, and quadrillions, and quintillions. So we're looking at about 73 quintillion videos could be uploaded to YouTube. And we could do something like, we could just play around with this a little bit. We could say, let's see, there are 60 seconds in a minute, and there are 60 minutes in an hour, and there are 24 hours in a day, and there are 365.25 days in a year. So if one video was uploaded every second, then YouTube could go for about 2 trillion years before they ran out of IDs. But wait, you say, there's more than that. I heard there's more like 400 videos per second being uploaded to YouTube. So let's go ahead and divide this by 400. And we've got here, YouTube could go for about 5 billion years before they ran out of ID numbers. I hope that's enough. I mean, maybe it is. But it's a very easy fix for YouTube. If it turns out that they start running out of numbers because people are just uploading videos at some prodigious rate, then all they have to do is increase the number of digits that they use. Let's say they go up to 12, and now they've just bought themselves a whole lot more time. Anyway, moving on. Problem number 5. An egg crate holds 3 dozen eggs. A farmer's flock of chickens laid 739 eggs yesterday. How many full crates will the farmer be able to fill up? Have Python compute the answer and assign it to the crates variable. And then finally, how many eggs are left over? Assign that to the eggs variable. So you come up with a calculation for crates, come up with eggs. I'll give you a hint. One of them is going to use division, and one of them is going to use modulo. Also keep in mind, we have an operator for doing standard division, and we have one for doing integer division. So you'll always get an integer as the answer. And just like before, I couldn't give you the actual answer in the assertion box. I couldn't just say assert crates equals whatever it is, 12. So I did a complicated calculation here just to make it less obvious what the answer is supposed to be. But you'll work it the same way. You press Shift Enter, and then if you get no errors, you know that you got your calculations correct. Okay, so that's lesson number 1. Now we'll move on to lesson number 2. Here we're going to learn about functions. Now, if you've taken some math classes, you probably know a little bit about functions. You know this, and if you did programming courses, you certainly know about functions, although in Java they would have been called methods. But you might have heard about these things. They're used a little bit differently in both contexts. Like a mathematical function is basically a calculation that you do that has a name. And usually in math, they're called something simple like f or g. Mathematicians tend to use just single letters for their, what are essentially identifiers or variable names, whereas computer programmers can use longer names. And so Python's the same way. You can use longer names for your functions, but we're going to be treating them kind of like in a mathematical sense. So a technical definition for a function is, it's basically a block of code, or you can think of it as being a box, that has an input that goes into it, a calculation is done, and then an output comes out. Okay, so here's a picture, right? So you've got some kind of rule that governs how the function works. You've got input going into it, the rule is applied, and then the output comes out. In programming, a function could be a little bit different. You might have an input coming into a calculation, and you might also have an influence from things like global variables or state variables or instance variables that are also affecting what happens in the function. And I want to use functions in kind of this pure sense, in which the only input into a function is just what's passed in as a parameter. Don't worry about any kind of global variables. It means that your functions are going to be relatively simple. They're only based upon the inputs, and they only produce one output. So in your math classes, you know, your functions were pretty simple and they were terse and compact, like f of x equals x cubed plus 5. But it does relate to programming in the sense that you've got a function with a name. Here it's called f. It has an input or a parameter. Here it's called x. It has a rule or a calculation, which is the x cubed plus 5. And then it produces an answer or a result based upon that calculation. But in programming, a function could have a more complicated or more complicated names. The parameters can have more complicated names, and the computations you can do can be much more complicated. So you can produce a function here called area that takes in two parameters, width and height. It does a computation on that width and height, and then produces an answer for you. So it's really kind of like two views of the same thing. So we're going to take a look at a few of the built-in Python programs, and then we're going to start writing our own functions. We'll look at a few of the Python functions, and then start writing our own functions. One of the built-in ones is called ORD. Its job is to take a single character of input and tell you what the ASCII or Unicode value is for that character. So the ASCII or Unicode value of capital A is 65, and for the euro symbol, it's 8,364. There's a corresponding function called char or character that takes a Unicode value and turns it back into a letter or a character. So I'll give you a couple of examples that you can try out. You can think of a function as being a way to map one set of values onto another set of values. In this case, the ORD function takes the set of characters that you can see on the screen and maps them onto a set of numbers. For every character in the input, there is a corresponding number in the output. So one-to-one mapping between those. And the CHR function does the opposite. It maps a set of numbers onto a set of characters that you can see on the screen. Again, there's a one-to-one mapping. For every one number you put in, there's exactly one character that comes out. The Base64 Encoder is also a mapping function. It takes a byte string as input, and it produces a byte string as output. So for every input string, there is a corresponding output string. Again, a one-to-one mapping. The length function maps strings onto numbers. It takes a string as input, and it produces a number as output. Here, it's not a one-to-one mapping. You've got the string Sierra College that produces 14 as the output, and there's other strings that also produce 14 as the output. So it's not a one-to-one mapping. It's a many-to-one mapping, but still it's a function that maps one set of values onto another set of values. Keep that definition in mind. That's really what a function is. When you write a method in Java or C, if you write a procedure in another language, it's all kind of like different names for the same thing. You are essentially making a mapping function, a map. It maps one set of values, the inputs, onto another set of values, the outputs. So I'm trying to like open up your mind a little bit and say there's more to functions than just like inputting and doing a computation and producing an output, right? When we really dig down there, what we're saying is we're writing a block of code that maps a set of inputs onto a set of outputs. And it doesn't have to be just one input. You could do two inputs, like area and width. That would map, the area function would map two numbers onto a single number. So in Python, you can define your own functions. use the keyword def, D-E-F, and then you give it the name of the function, and in parentheses you put any variables you want to use as inputs. If you don't want any inputs at all, then you just leave the parentheses empty, but you still put them there. And then here's where it's a little bit different from Java or C or C++. There's no curly braces around the body. Instead, you put a colon on the line with the define, and then you indent the body by just pressing the tab key. Actually, the notebook will indent it for you. And so the structure of a Python program is determined by how it's indented. And this looks strange to Java and C programmers because they're used to seeing those curly braces there. Python takes the opposite, takes a different approach, which is we're going to structure the program so it looks nice on the screen using a minimum of symbols. And some people either really like this or they really hate it. And it's sort of like a point of contention for Python programmers. Python programmers would say, well, you were going to indent your code anyway, right? So why not get rid of the superfluous or extra braces? For us, our functions are going to be really small. They just need to do one computation and then just return the result. So here's a function called f that takes in a single parameter called x. It cubes it, adds 5, and then just returns the result. This is very similar to that mathematical function that I showed you a couple minutes ago. And then here's one to compute the area of a triangle. It takes in the base and the height as the two inputs, multiplies them together, divides by 2, and then returns the result. So you can write a function definition in a cell. You need to execute it in order to load that function into the computer's memory. So I'm going to go ahead and do Shift-Enter. You can see the number appears over here to show me that I've loaded it. And then we can try them out. So f of 3 is 32. F of negative 5.7 is, there's the answer. And then we can compute the area of a triangle. We're really just using Python here as a glorified calculator. This is not much different than what your standard programmable calculator like a Texas Instrument or a Casio can do. With the exception here that our Python programs can be more complex and they can handle big numbers. Okay, problem number 1. Define the function shown here. I've actually done that for you. So to execute it, Shift-Enter. And then I've got a whole bunch of assertions here to ensure that the function was written correctly. So g of 1 should produce 19, g of 0 should produce 5, and so forth. So let's go ahead and execute this cell. And I got no errors, which means that my function is working correctly. Now, I'm kind of going at a fast pace here. If you get lost, you can always, if you're watching this video afterwards, you can always pause the video, go back and catch up, and then resume the video and keep going. So mathematicians call functions that invoke other functions as kind of like a function composition. And you can do the same thing in Python. A function can call another function. Here I've got a function called h that takes in a parameter n, and then it just takes 2 and multiplies that by f of n. So it takes the n that was inputted into the h function and passes that through to the f function. So let's go ahead and execute that cell and that one. And no errors there. Okay, so here's problem number 2, and this is the last problem on this page. Write a function called prism that computes the volume of a triangular prism from its base, height, and length. Now we already have a function that will compute the area of a triangle. We already have one that, given the width, and the height, will give us the area of this triangle. All we have to do is add on this length component. Well, not add it on, multiply it on. So we're going to make a function called prism that uses the try area function we already have, and then just adds on this last little bit to handle the length. So write your function definition in this box down here, and it'll start like this. It'll go define prism height, comma width, comma length, colon, press enter. You'll see it indents for you. And then here you're going to put return and then some calculation. Press Shift Enter to execute that cell, and then press Shift Enter on the cell below it and make sure that it works. Okay, so that's lesson number 2. Now the actual assignment. So this is the only file that you actually need to turn in. Now, Boolean expressions in Python. In Java, you use symbols like the ampersands to do and the vertical bars to do or, and the exclamation mark to do not. In Python, you actually just use the words and, or, and not. What a concept, right? So here is the expression A and not B or not A. And here's the expression itself written out. A and not B or not A. So if I execute this cell, it'll tell me the result of plugging true in for A and false in for B. By the way, in Python, the values true and false are written with a capital letter. So A equals true as a lowercase, that's not a thing. So it's got to be capitalized. So problem number 1 is determine a set of values for x, y, and z that would result in the expression evaluating to true. So here I've got a cell with x, y, and z all set to true. If we execute this, and we scroll up, we can see this is actually false. So we're going to have to go in and change, kind of by hand, each one of these values and see which one would result in a true. It's not that one there. Let's try changing this one. Nope, it's not there. Let's try changing this one. Oh, I got an error there because I misspelled true. Nope, that's false. Huh, there's got to be at least one. There we go, there's one. False, false, true. That produces a true. So you kind of just got to try all 8 combinations in order to figure out which ones produce a true. But we can automate that. So now we're going to see how Python does loops. In order to produce all 8 values of trues and falses, we're going to need 3 what are called nested loops. Loops within loops within loops. Here's how you do a loop in Python. Use the word for. Now this is not the same kind of loop you have in Java or C. This is a different kind of loop. So you do for and then a variable. Then the word in, and then a list of values that that variable can take on. So what this loop will do is it'll run 3 times. The first time through, the value 2 will be assigned to I. So the value of I will have the value 2. And the next time through, the value of I will be 5. And the third time through, the value of I will be 8. So the for loop in Python, at least the way I've written it here, is not your standard counting loop like it is in Java. This is more similar to what some programming languages call the for each loop, in which the value of a variable takes on each of the values in a list as you go down the list. So what this allows us to do is write loops that don't just count, but can actually iterate across different values. Here we're going to iterate across the values false and true, rather than 0 and 1. And the reason why we can use false and true is because those values can be plugged right into a Boolean expression. You can't plug the numbers 0 or 1 into a Boolean expression. It just won't work, right? You can't say 0 and 1 or 0. it'll give you an error because Boolean expressions do not work on numbers. They only work on true and false values. So here is a loop within a loop. We've got the B loop inside of the A loop. So the first time through, A is going to take on the value of false. And then the inner loop will run. B will take on the value of false. Then it will evaluate this expression, A and not B or not A, assign the value to out, and then we'll print out A, B, and out. So we'll get one row of output, one line of output. And then we'll go up and assign the value true to B, and then do the same thing. It'll plug A is false, B is true, A is false, and then produce a line of output. Now the B loop is done, and it will return to the A loop and assign the value true to A, and then run the B loop again. So the B loop will assign false to B, compute a value, print it out. It'll then assign the true to B, compute a value, print it out. And now the B loop is done and the A loop is done, and we've got our 4 rows of output. Let's go ahead and try it. So I'm going to execute this, and I've got a nice little table here showing all 4 possible values for A and B plus the corresponding output values. You may never have seen a program like this before. You may have never seen a program in which you've got a loop within a loop. And if you have 3 variables, you're now going to have a loop within a loop within a loop. Here's what it looks like. So we've got 3 variables, x, y, and z. Each one of them looping across true and false. Remember that every time you go inside of another loop, you need to indent one more level. So you can see here how they're indenting as we go down. And then these 2 statements, the one that assigns to out and the one that does a print, those are both inside of the innermost loop because they are indented to appear inside of this innermost loop. If so let me go ahead and run this. So Shift Enter, and then we get a nice little table here. If I forgot to indent the print here and I execute it, I don't get as many rows of output because the output line here is within the Z loop, but the print is not inside the Z loop. It's actually only in the Y loop. Okay, so this print only gets run every time the Y loop iterates, which is not every time, but it's every other time. So we only get 4 lines of output. So it's important in Python to pay attention to the indentation. If it's indented, it means it's inside that loop. If it's not indented, it's not inside that loop. Now, if you're familiar with the printf function from C or C++, Java even has one called printf, you can make your tables look a little bit neater by arranging them nicely into columns. So this is the same example as above, but instead of using print, we're using printf, and then stating that each column should occupy exactly 5, each column of output should occupy 5 spaces. And then we get this nice output that's all nicely lined up. Okay, problem number 2. Generate the truth table for this 4 variable expression. 4 variables. So a loop within a loop within a loop within a loop. Your loop variables will be called A, B, C, and D. So you might want to just take this one for 3 variables, change the variable names, add on a 4th loop, make sure you indent the computation of the output and the print inside of that 4th loop, so that you get a total of 16 rows of output. And then finally, for problem number 3, produce a table for this 5 variable expression you should end up with a table with 32 rows in it. So I have to be honest here. The lessons that we learned that involved defining functions and defining functions, we didn't use it very much in this particular assignment. But remember those lessons. I had to put the lessons dealing with functions up front because there's more lessons to do later on that more directly tie in with the Python assignment. So we didn't get a chance to use functions in this particular lab assignment, but keep them in mind because they will come up later. It might be a good idea before you do a particular assignment to go back and review some of the lessons from the previous ones just to refresh your memory about the concept that you learned. Once you're done with this, you're going to go File, Download As, Notebook. It's going to download this file to your computer, and then that's what you will upload on the assignment page. There will be a button here that says Submit Assignment. I don't have one because I'm a teacher, but make sure you upload to this page the file that you just finished, not the one that you downloaded originally. If you upload the one that you downloaded originally, it'll just be all blank, nothing will be filled in. I'll just mark it as incomplete and give you a note that says, it looks like you turned in the original one, please turn in the finished one. Okay, so that's it for a walkthrough of this week's assignment. 2 lessons and 1 file that you actually need to turn in. Now when we come back on Wednesday, so there's going to be no stream session on Monday because Monday is a holiday for us Americans. So when we come back on Wednesday, we're going to be starting in on Modular Arithmetic, which I think is chapter 5 in the book. We're skipping chapter 4. We're going to go into chapter 5. We're going to learn about a new way to do arithmetic and a new way to count using something called modular arithmetic. And that's going to start leading us into a whole section on cryptography. So this is going to be super interesting because by the end of this, by the end of about week 8 or so, you're going to be learning how to send and receive secret messages to other people in your class. So you're going to encrypt them using a secret key, and they are going to decrypt them. And when it gets encrypted, it just turns into garbage-looking characters that you can't read. But if you know the secret key to decrypt it, it'll just turn back into text. So it's really cool. And this is basically the same operation that allows you to encrypt data on the internet. You see that little lock symbol up in the corner? If we were to do something like, let's see, can we... Connection is secure, certificate. Let's look at the certificate. And open up and look at the details here. We can see the inside of this certificate, which is a way that the computers communicate with each other using encryption. You can see inside there are these huge numbers in there. And those are basically the secret keys that are used to communicate with the other side. Okay? So again, if you had trouble getting on to our Jupyter system, just drop me a note. I will reset your account. Your files will be preserved, but when you come back to the login screen, you'll just type in your MySierra username and then just pick a password. You won't be able to see it on the screen. You'll just see a bunch of dots. And so what I suggest to some people is open up a word processor or some kind of window where you can type in your password. You can see it, then copy it, paste it into the password field on Jupyter, and then throw away that file that exposes your password on there. That way you can be sure that you're typing in the correct password. Someday, since I run this Jupyter system, someday I will have the time to tie it in with our campus-wide authentication system. Then we won't have to worry about this whole password nonsense, right? But that's a project for the summer probably to work on that. Okay, so that's it for today. If there are no further questions, then we'll call it a day. And I will see you on Wednesday. But now, if you are tuning into the C programming class, that'll happen as usual on Tuesday. So Monday is the only day that we have off. Some high schools, some elementary schools in the United States take the whole week off instead of just a single day. And so we're at college now, and so we only get just the one day off. Actually, we also, technically, we get Friday off, but we don't have class on Friday anyway. So we get Friday and Monday off. Okay, everyone. I will see you next week. So take care. Okay, and then I just saw someone asked, is Python written in the C language? So Python is interpreted. So you type your Python program in, it goes into a standard text file, and then when you run your Python program, it is very quickly compiled into something called bytecode. And then that bytecode is then interpreted by the runtime environment for Python. So it's kind of like it's half compiled. It's not strictly interpreted the way something like bash commands are, or basic, old school 8-bit basic that runs on like these old computers. It's half compiled. There's a very quick compilation phase to turn it into an intermediate representation, and then a virtual machine takes over, or an interpreter takes over and executes it. Kind of the same way that Java is done, but Java Pythons are compiled as a separate step. Imagine if you could write your Python code and just hit run and it just starts running immediately, right? So it does the compilation very quickly and then runs it on the JVM. That's essentially what's going on in Python. So that Python interpreter is actually written in C. So there's actually several versions of Python out there. There's CPython, which is the one that we're running. The Python interpreter is written in C. There's also JPython, in which the Python interpreter is written in Java. So Python programs there can interface with other Java programs. So they can invoke the same classes, they can invoke the same methods that a regular Java program can. And then there's also JSPython, in which the Python interpreter is written in JavaScript. So there's a whole bunch out there. So the nice thing about having this separate layer of having an interpreter is you can swap out that layer with a different interpreter. Your Python programs still work the same, they're just now running in different environments. So the CPython runs kind of on the bare hardware, and the JPython runs within the JVM, and the JSPython runs in web browsers. When you come across a Python tutorial site, most of them are running JSPython, so the Python code is actually running in your browser itself. The Jupyter environment we're using for this particular course is running CPython on the back end. So your program is uploaded to a server, and there it is executed, and then the results are sent back to your browser. This allows people with fairly underpowered browsers to be able to do the complex kind of calculations we're going to do. If everyone had a nice modern computer with a fast processor and a lot of memory, boy, I'd love to just run JSPython, and then everything runs in the browser, and I don't have to worry about allocating computing resources for the Jupyter system, right? I can save a little bit of money that way by not having to buy the machine and buy the memory that has to run that system. If everything just ran in your browser, that'd be great, but not everyone has that. So this is the best solution we've got so far. Just kind of in a related question, the Java Virtual Machine, JVM, is also written in C. The PHP Virtual Machine, same kind of deal as Python, right? Your PHP scripts are compiled very quickly into a bytecode, and then that's executed or interpreted by the PHP interpreter, which is also written in C. And Perl is the same way. It gets compiled down into a bytecode, and that is executed by the Perl interpreter. So most of the time, these interpreters are written in a language like C or C++ because they want the best performance out of it. Now, the interesting question is, what is the Python compiler written in? I don't know the answer to that. I don't know what language the Python compiler is written in. I do know the answer to that for Java. The Java compiler is written in Java. Okay, so there's a Java compiler. It itself is written in Java. So a Java program compiles Java programs. And then it is executed on the JVM, which is written in C. How's that for mind bending? Okay, so your Java program, when you click on that compile button, another Java program takes over and compiles your Java code into the JVM bytecode. And then the JVM takes over and that executes yours. That one was written in C, but it's executing the Java bytecode. Are there any other examples of that? Like some old languages like Pascal. Pascal, at least on the old 8-bit computers, was done the same way. You might think of Pascal as being like a predecessor to Java in the sense that it compiled down to a bytecode and then that was executed by a virtual machine. So in that case, the virtual machine was also written in probably assembly language, but the Pascal compiler was written in Pascal. So that sort of leads to the question, how do you write a compiler in a language that you don't have a compiler for? Like, how is the first Java program compiled if the Java compiler didn't exist yet? And the answer there is, the first version of your compiler is probably written in assembly language. But it's a very simple one. You know, it might contain just enough of the language to be able to compile a slightly more complicated program. And then that one is able to compile an even more complicated program. So maybe your first version of the compiler only supports, let's say, classes and static methods. So no object orientation really to speak of. Just classes and static methods, and then your usual assortment of variables like integers, doubles, floats, and strings, right? If you had that would probably be enough to be able to write a very rudimentary compiler written in Java, which could then implement more of the language. Now maybe you could implement true object orientation with methods and objects and static and non-static methods and be able to define your own classes. And then maybe that version of the compiler could then compile the entire full language. So this is called bootstrapping a compiler. The first version is written in, you know, something that you have a compiler for, like assembly or even just hand compile it into the actual ones and zeros and then punch those into a file and then have the interpreter run that. I mean, that can be done. It's tedious, but it can be done. And then that version compiles an intermediate version of the language, and then that one finally compiles the full language. So that's how you do it. When I took what did I do? I took my compiler course, and there we wrote a compiler for it's called a toy language. It's not a language that exists only for learning about languages. And so we wrote that compiler in C. But then I started playing around with how do I get like a new version of the C compiler onto my system, especially on a system that doesn't yet have a C compiler. And then it walks you through. If you ever compile GCC from scratch and you don't have an existing C compiler, which is rare these days because most of the times you can just download a C compiler and run it. But if you had to do it from nothing and all you had was like an assembler, then it walks you through the whole process of bootstrapping the compiler on there. You start with a small program that's written in assembly language. You assemble that into an executable. You run that executable on C code that implements a slightly larger set of the C language, and that produces a second compiler that is now capable of compiling the whole language. Three-step process. Assembly language, then a minimal compiler, then the full compiler. So it's kind of cool to watch that whole process unfold. it's all automated. Right? You just run a script and it just does that whole thing. But back then, computers were slow enough that you could watch that script kind of grind through the whole process of, it would announce like, building minimal compiler, and then it would compile all the files for that, and then out would pop this thing, mini GCC, that could then compile the full language. Okay, so I think that's it for today. Thanks for tuning in. Again, we won't be here on Monday, but we'll be back on next Wednesday. I'll start talking about modular arithmetic. And on Tuesday and Thursday, we'll be talking about, what are we doing on Tuesday and Thursday? I don't know yet. For the C class. Something about arrays, I think. Oh, pointers. That's right. We're getting into pointers next week. So don't miss that if that's something that interests you as far as programming goes. Okay. So I'll sign off for now. Have a great weekend. No, not weekend. Yeah, have a great weekend if that's it for this class. If you're coming back on Thursday, I will see you then. Take care. Bye-bye.